Sir, it is started.
Thank you. So good afternoon, everybody. Welcome to this last lecture of this module. And today we will discuss one approach to solve various kinds of constraint optimization problems in economics, and one of the most widely used approaches which are used for economics. The reason is that economics problem solving, the problems are very complex, and being very highly complex problems, their optimal solutions are often impossible to get. We have discussed various kinds of anytime algorithms, contract algorithms, time-bounded algorithms, etc. But all these algorithms that we had discussed from the state space transformation model moved from a partial solution space to slowly finding the goal. Typically, our states transformation rules moved from an initial state where the solution was not formed, and slowly the solution was getting formed, and which was the G-like component, and then at the goal the full solution was formed. Today we will discuss the other approach, which is again typically time-bounded algorithms, often not time-bounded. Many economics problems, even sometimes what is the optimal solution is not known. It is so complex. So here, for such very complex, multi-dimensional, multi-criteria problems, we have another approach. This is the solution transformation approach. The solution transformation approach goes from solution to solution. That means while in our state space approach, we started from nothing and slowly built up the solution, here we start with a solution. Any solution that we can obtain by any mechanism. It may be a valid solution, it may be close to a valid solution. And then we apply transformations to get a new solution from this solution. So this is a different strategy where we move from solution to solution. This is a poorer quality to improved quality. And in some cases, the solution or the solution that we create may not be fully valid. May or may not. Most cases it is, sometimes it is not. The most popular method used for doing this is called local transformation. Or local and local search. That means you have a solution S1. This is a solution. For example, you are solving the resource allocation problem of the problem that we talked about. There are K bidders. There is a piece of land which is to be distributed between multiple parties. You do a random allocation. So you start with a random allocation and create a solution. Then you apply a transformation to get typically a new solution S dashed. Now this is by a local change. This is not like our state transformation rules where we look at all possibilities. Here you don't look at all possibilities. But some possibilities. For example, you have your land allocation problem. So you have L and you randomly do an allocation and determine what is called the fitness of the allocation. Then you apply a local transformation. One example of a local transformation could be exchange. You exchange two allocations. And as soon as you exchange two allocations, you get a new solution. And then you go on doing this in some systematic manner. Repeat in some systematic manner. Now here, the systematic could also be stochastic because the space is so large that you would like to explore that space. So this space is a little different from our original state space. Here we are moving from solution to solution. Each of them is a goal. Each of them is a goal, but one goal may be better than another goal. So you move in this space, and how do you intelligently move in this space? So have you got an idea that we do a random allocation and then we do a local transformation? Again, we look at what we have obtained. We do a random allocation, we do a local transformation. We do a random allocation, we do a local transformation. And go on doing this in some manner. Any questions here by anybody? Is it clear, Adhiraj Rastogi?
Yes, sir.
Yeah. So among the methods that are deployed for this local transformation, two methods are quite popular. One is called Taboo Search. In Taboo Search, what you do is you look from one particular state, you look at the 10 options that you have for local transformation. Or among the 100 options, you shortlist 10. And you see which one gives you an improvement. But while going to the next state, you also have a sequence, a taboo list. A taboo list consists of a list of states that you have recently visited, which means that you maintain a small list of states that you recently visited. So what you do is you make a local transformation to one of the best states in the local vicinity, except those which are on the taboo list. And as soon as you do that, you obtain a new state and you update the taboo list. And you go on doing this for some time. Taboo search is a very, very popular mechanism recently, maybe a few decades, but it has become a very popular mechanism for solving various complex problems. Along taboo search, you employ another method, which is known as simulated annealing. In simulated annealing, what you do is now which is the next state that you choose? is chosen with a probability. So among the 100 possible next states, you shortlist 10, and among these 10, you don't necessarily go to the one which yields the best minimum cost now. You go to the one which yields the best minimum cost with a certain probability. That means if there are 10 top elements, you give more priority to the one which is improving the most, and you give sequentially you give less priority to the other ones, and that probability distribution is known as, anybody knows what it is called? It is called the temperature. You know, when we do cooling, heating, we apply the temperature is the variational gradient that you can allow. That means how much probability. Somebody is speaking. Can you mute, please?
Zero, you know, 0 KY60. ये गलत क्यों लिखा है बार-बार?
Yeah, thank you. So there somebody is busy doing something else actually. So the temperature that you have is the probabilities that you assign. Maybe initially among the top 10, you give everybody equal probability. And then as the search proceeds, the probability assigned to the one which is smaller increases. So if you apply pure local search, then you can get stuck in what is called a local optimum. If you apply pure gradient descent search, then you will end up in a local optima like situation. Have you understood? Let me explain this with a small diagram. Suppose this is your optimization function space with local transformations, and you are here. If you apply this one, you will go down. By gradient descent, you are going to the lowest possible. Now, you may go down here, but here there is no chance of going down, and you may reach your solution. But in another space, which is like this, you may get stuck here, whereas your optimal lies here. So what you do is you allow a probability of going to not the minimum. That means you allow a probability of going beyond the minimum with a certain level. And then you vary this. Initially it is high, it is quite randomized, and then slowly it quenches and goes to the, and slowly recedes to 0 and becomes local. That way there is a proof that this method eventually, the proof is it eventually leads to the global optimum. How many of you heard of simulated annealing before? Please raise your hands. Nobody? None of you did simulated annealing method before? True? Nobody?
No, sir.
Okay. So you should read it. This is a very seminal paper. The simulated annealing paper, which came out long ago, is a very seminal paper which proved, and then this has been used in a large number of applications. economics being one of them. Taboo search is a more recent method, but that has also started finding applications. The third and probably the most popular method of solution transformation is the genetic algorithm, which we shall discuss in more details. And the fourth and fifth are many. There are particle swarm optimization, etc., etc. All of them are for very, very complex optimization. Particle swarm optimization, ant colony optimization, etc. There are hundreds of names, especially because you have got such a variety of problems. Nowadays, also optimization based on deep neural networks have started. How can I combine deep neural networks, which are used for defining the quality of the solution or the solution trend, and combine it with local transformation? With this, are you getting an idea how it can be used in economics from this problem? Any of the economics problems that you do, you find a solution and then you go on improving the solution. And then you use any of the 4 or 5 methods that we have discussed. Any questions till now? Okay. Shall I proceed? Just tell me yes or no.
Yes, sir.
Okay. So now we come to genetic algorithms. All, whether it's neural networks or whether it's genetic algorithms or whether it's simulated annealing, all of them have been inspired from natural systems and natural processes and the way natural systems grow. Genetic algorithms are this sort of temperature changing is used. Where can you tell me? In experimental science, crystal formation, and several other places. So the genetic algorithm is the other one which we shall quickly discuss, which is inspired from evolutionary biology. And here it is based on natural selection and the best performing individuals. The whole concept of the best one, survival of the fittest, that concept has been used. And it has been solved again for a large number of problems, whether in optimization design. It has got, how many of you know the genetic algorithms at least? Have heard of genetic algorithms? 2, 3, only 3. Okay, so genetic algorithms has got these 3 basic steps. One, by the way, most of these slides except the first one was prepared by Colonel Ashutosh Verma. So I just want to thank him for helping me out. So they encode possible solutions in an initial population. Now, the difference between the others and this is that I don't work with a single local solution, but I work with a population of solutions. I work with a population of solutions and I create, instead of one more solution, I create the next population. So the difference between the previous local searches, which was working on single solution to solution transformation, this is solution set to solution set. So this is how it proceeds. Now, the steps are encoding a possible solution. What is the encoding of a solution? How do you create the first set or the first generation? And then how do you create new generation? So the new population generation is created by these four components. One is the joint component of crossover and mutation. As I said, it is inspired from biology. Then there is the fitness function. We don't call it the cost because sometimes the cost, it may not be a solution itself. So we combine the cost of the solution with whether it is a solution or not to define what is called the fitness function. And then we have a method after creation. So this is used to create the next possible pool. And we'll discuss in a while how this is done in brief. And then from this next possible pool, you identify who all will go into the next solution. Who all will go into the next solution. So let's see how it happens. The easiest way of defining a solution in genetic algorithms, if you know nothing, is a binary string of features. You identify the features of a solution, and then among all possible features which can combine to form a solution, or all possible aspects, you do a binary encoding of whether this is there or not there. Like in the traveling salesman problem, you can say whether this edge is there or not there. So you have got, if there are n nodes, then there are possibility of, in an undirected graph, there are possible NC2 edges. Alright, because there are possibility of NC2 edges, you will create a vector like this of NC2 size, and you will assign 0 and 1. And if you assign 0 and 1, you first see whether it is a solution or not. If it is not a solution, then obviously you will assign it a poor quality fitness value. And if it is a solution, then you know what is the cost. If it is so, you can define a string to be a solution, and each individual string is a solution. The solution may be valid, the solution may not be valid. And then you, for every such string, you define a fitness function. So this fitness function is a composition of whether the solution is valid and what is the cost. You do a combination of these two in some form and create a fitness function. So maybe if you have just randomly assigned some edges in the traveling salesman problem, you check how many, firstly, no edges will be repeated first by this. But from this you can calculate how many nodes are visited. How many nodes are visited exactly once, how many nodes may be visited twice, etc., etc., etc. And you can create a solution. Now each string is an individual solution. It may be, you may also work only on feasible solutions. So you may randomly generate feasible solutions. And then what you do is, given, you create what is called a pool of feasible solutions. And this pool is called a population. So this is inspired from biology. There is a population. So what this picture shown here may be an initial population. And in traveling salesman problem, you will randomly generate some 1000 such possibilities. You will throw away those which are not solutions. And you will only look at feasible solutions and create the first population. Is it clear up to this point? Anybody has a doubt? Good. Then you apply crossover and mutation. Crossover takes two parents and produces one or two or more children. Typically, two parents produce two children. So first part is select two parents. Then for a definition like this, you identify a splitting point. And the splitting point is identified in such a way that based on this splitting point, you can split, exchange, and create new solutions. Here, from this parent and this parent, this one splitting point is here, this one splitting point is here. Sorry, this one splitting point is here. This one split here, this one is split here. Now, often many times they split in the middle, but that is not necessary. You split each parent at a splitting point. And then you have got 4 parts: x1, y1, x2, y2. Then you combine these 4 points, these splits, one from this side and one from this side, one from this side and one from this side. Here I did y1, x2. I could have done x2, y1. Here I did x1, y2. I could have done the other one. Somehow, typically you may create 2 new children. This is crossover. Mutation is from one element you mutate 1 bit. These are called genes. These zeros and ones are called genes. So you mutate 1 gene, make it 1 to 0 or 0 to 1. Small random changes in the string. So the whole process is you do a crossover and a mutation, and you create 2 new children. So what you do is you do a crossover and mutation, and you create new children from the old population to the new population. Any questions? Good. Then you have a fitness function. Based on the fitness function, you rank the values. Given the population, you rank them on the fitness function. And you rank them in such a way that they are in rank 1, 2, 3, 4, 5, 6. Some of them, and from this rank, you find the average fitness value. And from the average fitness value, you will be able to find the distribution of solutions. The main thing that we are interested is diversity of solution and not getting stuck in the whole population becoming similar. The costs may be similar, but the strings should not be similar. So what you do is you have this fitness function. So now let us see our process. Any questions till now? Anybody? Anybody has a question? Jyoti Pandey, are you there? Jyoti Pandey, are you there?
Yes, sir. Yes, I'm there.
It's fine. Have you understood?
Yes, sir.
So now let us look at this problem. This is taken from one of our own faculty members, my good friend, Professor Vishwajit Mahanti, in the Industrial and Systems Engineering Department, from whose work this case study has been taken. Suppose there are 4 factories supplying goods to 4 cities. Each factory can supply to only 1 city, but we have defined that each factory, and each city can get supplies from exactly 1 factory. The distance between the factories is given in this table. The object is to minimize the distance. This is like our traveling salesman problem, but a slightly different variation where we are doing a supply assignment problem. This is not a tour problem. This is a supply assignment problem that each factory will supply. So you have got factories and you have got cities, and you want to do an assignment, a matching. and you want to find the minimum matching, the matching which minimizes the total distance. And you have these distances between factories. Straightforward problem. Can be solved by heuristic search, can be solved by many methods. So here is an assignment. Our permutation or our encoding or our population or our gene, our elements or our single chromosome is defined like this. Each factory 1, 2, 3, 4. This is factory 1, this is 2, this is 3, this is 4. And then, sorry, this is city 1, 2, 3, 4. These are cities. And which factory serves which city? And we want to make sure that there is no duplication in the name of the cities in this list, because that is our feasible solution. And as soon as we do an assignment, we get the distance from the distance matrix, we get the cost. This is a simple problem. Suppose we can generate how many initial solutions?
4 factorial.
4 factorial. Yeah. So if we want, we will generate this is just a case study to just demonstrate what we are doing. So we are going to generate an initial population, and here our initial population consists of these 4 elements randomly generated. Object is to minimize the total distance or maximize 100 minus d. So this is how we do a fitness function of 100 minus d. So based on this initial population, we find the fitness function for all solutions 41, 14, 44, 36. The average of the fitness function is this. Then we rank them. Once we rank them, the one with the highest rank is duplicated. The one with the lowest rank or that which is below a certain threshold is removed. And the next set, that means now by removing a few and duplicating a few, we create the pool for crossover and mutation. What do we do? Crossover can be done in many ways. In this case, we define a crossover as moving some element from one, so taking 2 elements of one parent and 2 elements of another parent and forming it. So for example, this may not yield a solution, feasible solution, so we have to transform it. So you have to create a crossover in such a way that a proper solution is formed. So here, by some movements, I have created from these 2 parents, I have created these 2 children. As we saw, we had replicate in the best elements are then the best few elements are replicated into the new population. The others are going through a crossover to create a new pool. How does mutation occur? Now mutation, given the pool for crossover, you may replicate and mutate. So you can apply crossover mutation, you can apply only crossover, you can apply only mutation and create the next pool. There are millions of variations that you can apply in genetic algorithms. Once we have created the next population, which is this, we again find the fitness function of each. Find the average. Again, whichever is the lowest we reject, whichever is the best we duplicate, and the others we continue for the next round of population. Create, again do crossover and mutation, and go on doing this for many generations. Typically, you have to create a large diversity of population, and you have to go through many generations, because if the problem is small, then genetic algorithms are not required. Genetic algorithms are typically required for problems which are very, very complex, whose space is billions of nodes, and where we want to get a time-driven algorithm. So if depending even on your time, sometimes you decide on the combination of population and generation. How do we extend this to multi-objective? Because this is where it is very popular, and this is where my very good friend, my batchmate at IIT Kharagpur, whose most famous algorithm is now in the US, Professor Kalyanmoy Deb, who was then at IIT Kanpur. He's my batchmate at IIT Kharagpur in mechanical engineering. His brother is Professor Devashish Deb in mining engineering. So he developed this concept of non-dominated sorting genetic algorithm, the version 2, suggested in 2002. And this is probably the most cited engineering paper that has come out of authors in India in a long time. So again, here he works on the Pareto or non-dominated optimality. So we have discussed the non-dominated set earlier, and the objective is to find the Pareto set. We know that when there is non-dominance, you cannot necessarily identify a unique best. The whole best set, the rank 1 set, is the non-dominated solutions. All non-dominated solutions will form rank 1. So what you do is you now have rank 1 is one set, rank 2 is another set, rank 3 is another set. You create rank sets. And from these rank sets, so in the population, the chromosome definition, the problem identification is identical. The chromosome definition is all identical. Only the objective function is multi-objective. The objective function being multi-objective, the fitness function itself is also multi-objective. The fitness function being multi-objective, you cannot find a unique, you cannot rank them by a total order. That is 1, 2, 3, 4. Rank 1 will be a set. Which set will it be? Can anybody tell me which set will it be?
Pareto optimal.
Yeah, it will be the Pareto optimal set. So how do you define ranks? You define ranks by Pareto optimal sets. So what you do is you define rank 1 as the Pareto optimal set. Then you remove that, and then you find the next Pareto optimal set. You find the next Pareto optimal set. That is rank 2. You remove that. You find the third Pareto optimal set. That is rank 3. You remove that. You find the fourth Pareto optimal set. That is the set of solutions of rank 4. Now, among the problems in a particular rank, you choose a few of them. So you have found some problems of rank 1, some problems of rank 2, some of rank 3. So from here, you choose one of a few of them. And to choose a few, you use the concept of a crowding distance. That means if two are very close, you choose one of them. If two are far away, so you try to define a region around a point, and you see within that epsilon region if somebody is there or not. Then you choose only one of them. So among the people of the same rank, you selectively choose a few. Similarly in the second rank, similarly in the third rank. Why are we choosing all these ranks? Firstly, because each rank is non-dominated set. They are not comparable with each other. However, rank 2 are all better than rank 2 are worse than rank 1. That means rank 1 dominates rank 2. But we choose a small set from rank 1, a small set from rank 2, a small set from rank 3, etc., for our next purpose. So here is the method. Again, encode in a population, initialize the population. Then you do this elitism selection. That means you try to choose good ones, like we did before. Then you apply crossover mutation. So you bring the few best individuals from previous generation. And these best individuals are chosen from this rank set. To do this ranking with this fitness function, you use this method of I just described of non-dominated sorting and crowd distance calculation. Then you prepare the next generation. So now this is exactly what happens. You first suppose these are two objective functions. Can you tell me whether we are minimizing or maximizing objective 1 and 2, or what are we doing?
Sir, minimizing.
Minimizing both.
Yeah, we are minimizing both. In this case, we are minimizing both. Got it, everybody? Very good. We are simultaneously minimizing both. If we are maximizing both, the plots will be in that other shape. So this is rank 1, this is rank 2, this is rank 3, this is rank 4. So you create these ranks, and from rank 1, out of these two, you may just choose one of them. And this one you choose because this is farther away. So there are various functions for crowd distance calculation, and we know that the lower rank is a higher fitness. Based on this crowd distance calculation, you create the new pool. From there, you do the same crossover and mutation and proceed. So this small modification has been so widely used that it is probably one of the most popular algorithms ever. Before I conclude, Kalyanmai and some of his students used this multi-objective evolutionary algorithm for a land use management problem. What they did was they had three objectives: maximize economic returns, minimize carbon footprint, and minimize the net soil erosion. They encoded this in a 2D grid, 3D grid, where the land was in 2 dimensions and time was in the 3rd dimension. And then they looked at land patches, and for every patch, they decided what land use it will be for. So they have to choose the land use for different patches. And in order to compute the fitness function, they had all these inputs for all these pieces of land. And they ran this for 5,000 generations over huge populations for over 85 hours in 2006, which would have run for about maybe 8 hours now. And they obtained solutions. This is just a pictorial view of what they did. And they compared it with pure local search. And they found that their method gives much better solutions than pure local search for approximately the same amount of time. So this is one example of how they have used what they have done. So with this, we come to a summary of this module. And in this module, we have discussed multi-objective, multi-dimensional, and to some extent multi-party, but this is not fully done, partially done. So it was single or multi-objective, single or multi-dimensional, single or multi-party. And here we have seen various kinds. We have seen modeling. And in modeling, we have seen state space modeling, where we had fully visible or partially visible. Then we saw deterministic, non-deterministic, or probabilistic methods. We also briefly looked at probabilistic reasoning using belief networks. And we saw heuristic search in deep details, where we looked at algorithm A star, IDA star, MDFBB, right? Then we also looked at any other names that you can recall? Anything else you can recall?
Alpha beta pruning.
Alpha beta pruning for multi-party. Then we saw belief networks. We discussed local search. Briefly talked about stochastic search. And we also looked at evolutionary or genetic algorithms. What we have not discussed in details is detailed logical deduction. That requires a lot of, for economics. That requires a lot. We have not discussed this. That requires a lot of other background. We don't have enough time for that, and that is, and we have more important things to discuss in the subsequent modules, which are more relevant, which are very modern. But this sort of logical deduction for economics finds deep play in works of a lot of Nobel laureates, including Amartya Sen and others, and various others. So, Pulak, would you like to give some concluding words for our session for this module?
Sir, before we conclude, if they can say about their experiences, particularly the convergence between economics and artificial intelligence, whatever we discussed in this course so far. I mean, one or two problems, if they can highlight from their side, which can possibly be analyzed or solved by using AI.
Yeah, well, let us hear from them.
I'd be very much interested to hear from them if they have thought of any such problem. What can potentially be solved or analyzed by using AI techniques?
So, anybody would like to say anything? Pradipti Thakur, are you there?
Yes, sir.
So, what is your feedback?
Sir, like in this particular module, like we learnt about a lot of different problems in economics. A couple of them were based on like land allocation, resource allocation, and also about how a farmer can make their crop decisions. What would be the right way to do that? Also, we also learned a little bit about how strategic decisions can be made by firms. That was also one point. I think uh, I think we found a lot of problems, sir, that we could solve. Like I'm not an expert in economics, but I think there were a lot of problems that we discussed throughout this module.
Thank you. And you can map them to some of these methods at points in time.
Yes, sir. Yes, sir. Yes, sir.
Thank you. Anybody else?
Hello, sir.
Yes.
Sir, when you were teaching the AI methods and the AI algorithms, I felt that there should have been more focus on solving economic problems rather than because we were just solving problems that were just in AI domain, but we haven't like uh, fully
Yeah,
understood
but
how to apply AI in economics.
unless you know the method, unless you
Yes.
know the details of the method, how will you use that method? Then you will use it as a package. One is to
Yes, sir,
use
that
things as a
I
package.
got it, but one problem that I had during the test as well was that I wasn't able to apply much of AI in those questions that were there.
The first
Yes, sir.
question was full of modeling, no?
Are you
Yes,
talking
sir.
about part B? Are you talking about part
No, sir,
B?
part A, part A.
Okay.
In part A, you have to convert it to see many of the problems finally end up with deep mathematical problems, isn't it? So then you have to know the mathematics, you have to know the algorithm. Some of the algorithms
Sir,
that
sir,
the
maybe from the
Gale-Shapley
next
algorithm.
time,
The
sir, maybe
Gale-Shapley
from the
algorithm is
next
an
time,
algorithm. It's the alphabet, it's a matching algorithm.
sir, if you could provide us with some practice problems before the test or during the course as well, so that would be very helpful for us.
Yeah, I can give you a list of problems that you can solve.
Yes, sir.
Yes. So for other modules, we will keep this suggestion in mind. Basically, a list of problems where you can apply the AI techniques before you write the exam. I think this is what you are suggesting, Shivam, right?
Yes, sir. Because, sir, before the test, we haven't like solved any of the problems, like so we weren't aware how to solve them in the question paper as well.
Okay.
Yes, sir. Same thing happened with me also.
Yeah, then you need tutorial classes other than what is there in the course. Otherwise, you have to shorten the course content also. That is one possibility.
Okay. So, sir, what we can think of subsequently, maybe for next year, say out of 9 or 10 lectures, we can speak in 7 or 8, and 1 or 2 maybe kept for.
Yeah, we can pre-record some of the lectures so that
Yeah.
they can watch it and come.
Right, sir.
That may be helpful. Now,
Yes.
Professor Naik is also there. Professor Naik, do you have any thoughts?
So, Namaskar, sir. So I just joined. I was attending another meeting, UGPC. So,
Okay. So, any other point from students?
Sir, I would just like to add one point. In the course, we have tried to see, from economics perspective, we have tried to see problems from 3 major players. So one is from the farmer's perspective, like crop choice decision. Like say from farm's perspective, one question was there in the class test. That is basically there are various options of sourcing technology, which option the farm should go for. And the third one was basically in respect of deciding the tax rates across alternative products, alternative petroleum products, where there is some degree of substitutability. Like say petrol versus diesel, for example, in transportation. So whether high rate of tax on diesel, that is what we discuss, that high rate of tax would basically raise the transportation cost, and there would be switching of consumers or users rather from one mode to another, or what may be the implication for cost. All these issues we discuss. But again, high rate of tax on petroleum products, whether that will have some consequences. So these are some of the issues that may be framed in the perspective of as you are pointing out, multi-objective, multi-dimensional, and multi-party optimization problem, because here there are several actors. In fact, the government is there, the farmers are there, when diesel is used for irrigation purpose, then transport section is there, when diesel is used for vehicles, for commercial vehicles, and again there are individual or private vehicles when petroleum is used. So that sort of problem is there basically from government's perspective. Like as you are discussing about allocation of land, when the government is allocating land for alternative purposes. So three stakeholders primarily we discussed, but as you have rightly pointed out, we have discussed about these problems, not focusing so much about multi-stakeholders in a particular problem. We have talked about different problems for different, primarily for different stakeholders, but we didn't discuss about role of different stakeholders or objective of different stakeholders in a particular problem. So
yeah, Pulak, let me since you have stated that, let me tell people where is the interesting issue there. So firstly, our problems are all like this. Our problems are, you have got a set of slots, whatever they be, there is a set of slots. You take any problem and you have got a set of elements, and you can map these elements to these slots, correct? Whether you call it petrol, price allotment, diesel allotment, whatever, you're assigning some values to these slots based on. Now, for different parties, P1, and you have an objective, and you have an objective function, O1, O2, O3, On. These are my objective functions. Now I have got multiple parties, P1, P2, Pn. Now, when I create a Pareto front, that means if I create a solution S1, each party has its own way of defining their objective.
right, sir.
That means the compositional of these this set O, for this fellow will be F1, for this person will be F2, for this person will be Fn. M, let us say M parties. So each has their own function. Therefore, whenever there is a situation, each player applies their own function to come to their bidding or to their decision or to their selection.
Right.
Now, so each function here mathematically is a total order on this multiple variables. So each of them can linearize from here, but the linearization, the ordering of P1 and the ordering of P2 for the same set may be different. Up to the order, so everybody will have their own ordering. Once everybody has their own ordering, these are called preference predicates. Their own orderings are called preference. I didn't go into all of this because we didn't have time and there are so many other topics to teach, but this is a very interesting topic. Once you have preference predicates, then how do you create a game tree where everybody has their own preference predicates? Some of the items are common. So this is a game tree under a partial order. This is a new concept of a game tree. So then you can define this this is a game tree solution under individual preference predicates. We can model this problem sometime later and use it and map this to an economics problem. This is a very, very interesting topic on its own. And the whole of this alpha beta pruning and all that pruning changes completely.
Right, sir. I mean, this would be really very interesting problem actually, particularly when individual preferences or preferences across stakeholders differ, then making a collective decision. I mean, how to make a collective decision.
Yeah.
So, sir, what I'll do for next batches for this module, I'll also see, I mean, how these the problems from economics, how they can be redefined to incorporate this perspective, this multi-stakeholder perspective, as you have, sir, rightly pointed out. That probably needs a little bit more focus while defining the problems. I'll do that.
Exactly. It's a very interesting thing. And let me see if I can extract out the material that you want, because that is very close to my heart. So let me just do a little bit of surprising. I normally don't like to do this, but let me see. Just give me a minute, Pulak. I will.
Yes, sir. Yes, sir.
Is my screen visible?
Yes, sir.
Yes, sir. Yes, sir.
So this is the work that we had done. Pallab Dasgupta, myself, and Professor Desarkar had done in 1996. So this is exactly what you're saying. The problem of partial order game tree arises from game playing, where multiple conflicting and non-commensurate ideas decide on the merit of a game. In a partial order game tree, outcome evaluated to the tip are vectors, where each dimension of the vector distinct criteria. This leads where every game playing strategy of a player, several outcomes. So everybody has their own strategy, and then you show what kind of solutions happens, what sort of an algebra comes out, etc. It's a very interesting problem.
Right, sir. Right, sir. This should be really very interesting. So also from economics point of view, we also need to redefine the problem in this direction, bringing in more insights about.
Are students getting an idea of what this is about? I just
yes,
want to know. No, I'm asking the students. Are they there, or have everybody left?
So is it about multi-party and multi-objective optimization?
Yes, multi-party, multi-objective games where each party has their own objective function from a common set of objectives. That is the problem which Pulak was just trying to identify. Very interesting problem.
Even this can be applied to the farm laws.
Yes. I know all of it. We did not get time because I don't have economics funda, na?
Sir, I had a question on that. So,
yes,
like, given a set of, inputs, all the parties, all their respective objectives, etc. So we have all the information. So does the solution is deterministic? Does the algorithm boil down to a single specific solution?
In a multi-objective, this one, it is never a single solution, no?
If we perform the optimization procedure on top of it.
Even if you perform, if I have got two objectives, cost and time, you are there, no? You have seen that how one solution does not dominate the other. We discussed in details, non-dominated.
Yeah.
So you cannot create a single solution. If you could, then probably all life problems would have all become very easy.
Yeah, that's true.
Sir, may I just add? In fact, there are examples like, say, dual pricing in telephone services. What it was earlier. During daytime, the call rate used to be high, sir. When I'm talking about late 90s, STD tariff, the rate was different. after 9 o'clock in the night versus during the daytime.
Pulak, let us do one thing. You make a list of such problems. Let us
Right.
model all of them so that we can share it with the students.
Yes, sir. Yes, sir.
That way, I think the questions raised by Shivam will also be partially answered. Right, Shivam?
Yes, sir.
Yeah, there are sir, many such examples. I list that out. For example, electricity, commercial versus domestic users.
Yeah, the question is that we know solutions to many methods, general methods, but we are not experts in problems. Whereas you are experts in problems and you all generally apply a package. But I think, we can have very good solutions for various kinds of problems using these methods.
Right, sir. Right, sir.
So,
I'll make a list, sir.
okay, thank you, everybody. It
Sir,
was a
Professor Naik
pleasure.
is there if he wants to add.
Naik?
No, I think I heard all that as Pulak, you are going to give a list. Maybe I will. We can together suggest a few. I think I'll.
Yeah, we will make a list of problems of various gradations and share it with the students.
I mean,
Sure,
from
sir.
the public policy perspective, we can have quite a few.
Yeah, even stock trading, portfolio management, you can get a lot. Even the students can raise a lot of questions and come up with various kinds of problems. And many of these are very new problems have come up. A lot of new problems have come up.
New problems and new, sir, also new constraints. The constraints are also becoming very complex.
Yes.
So
That is why these evolutionary algorithms are now more and more used. Okay, then